Hello and welcome to Textbook Engineering Problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition, and we're doing problem number 4.73. All right, problem statement says a mixture of propane and butane is burned with pure oxygen. The combustion products contain 47.4 mole percent water. After all the water is removed from the products, the residual gas contains 69.4 mole percent carbon dioxide and the balance oxygen. What is the mole percent of propane in the fuel? Okay, so we've got this process. First, we've got a kind of like a furnace here, and then we've got a dryer over here. The first thing you want to do is make a diagram like this and then label out the things that they gave you. So they gave us these pieces, right? So what you need to do then is, the first thing that I did was calculate this from this. Now you can do this, I don't know, I could kind of do it like intuitively, but then I wanted to try and break it down. And so I broke down like the math right here of how you would calculate what these things are. Basically, you just have to say, okay, there's this much moles of N4, and it's less than N3 by however much water is in there, right? Okay, so then you can convert that to this, and then you get this N4, N3 ratio, and then you can plug that into this equation over here that we did before, okay? And then you can calculate, hey, this is what your oxygen concentration is in stream 3. Okay, and then if you know concentration in stream 3 of the 2 components, then you can just get the third one for free, right? 1 minus the other 2, okay? So not too difficult to do that one. Now that you've got all of these known, the rest of this problem becomes a lot easier, okay? Okay, so after that, we write down our chemical reaction equations here, and then we assume that the combustion goes all the way to completion, okay? You don't have to do all of these balances that I did, but I just do them all out of habit. Okay, so I did a carbon balance on the reactor, and then I did a hydrogen balance and an oxygen balance. I ended up only using the oxygen balance in the end. Okay, so this one comes back and ends up being important. This one is just, these other two ones you don't end up using, but I mean, you could, but you don't have to. So there you go. Okay, so then we move on to the reaction equations, okay, and we do extent of reaction equations. And the general extent of reaction equation is here. We've got our 2 reaction equations, okay? So then we start writing them out. We say the amount of propane in here, the amount of, equals the amount of propane we started with, minus the extent of reaction. It's minus because it's a reactant, okay? Yeah, you have to pay attention to these stoichiometric coefficients, okay? That's the biggest part that you can accidentally mess up on. I almost messed up on this one right here because I almost forgot the 1/2 there, okay? Because it's important to have the 2, right? The 2 there, okay? Anyway, we just fill, oh my goodness. We just fill all these out, right? Extent of reaction, just follow the formula, right? You just plug them all in. You solve for what these extents are. You solve for what those extents are, and then you can just plug in to get rid of the extent of reaction, right? Because we don't know what the extent of reaction is. So it's easier to just work in N2, put everything in N2 so that everything's on an N2 basis. Either that, or you could just choose that you want to have like a certain basis, like, hey, I'm just going to solve everything as though N1 is 100 moles or something like that. You could do that too. Sometimes it makes it a little bit easier to do it that way. Okay, so then we've got our 3 extent of reaction equations because we used 2 of them this one, and this one to get rid of the extended reaction and put it in terms of N2, and then we just had 3 other ones, right? We had O2, CO2, and water. Okay, and then all those kind of filter over here. Okay. So we've got these 3 equations. Okay, so then from this part, I just basically rewrote these equations here, the same ones that we did over here. And then I said, okay, I want to put this on an N2 basis, and then I don't necessarily want to use this equation right away, because that one's like the more complicated one. And I have a simpler equation that has these unknowns in it, which is this one right here, right? So I'm just going to use 1, 2, and 3. Okay, so I don't have to use this other balance that makes things a little bit more complicated. Also, I think if I used all 3 of those balances, if I used this one, and this one, then it wouldn't be, they're not independent, I don't think. So if you try to use all 3 of these, they wouldn't be independent. You'd get something like 0 equals 0, which is true, but also not very useful. So you'll want to use like a process variable or a process equation, okay, in there, so you don't end up with something that's useless. Okay. This right here is like a matrix that I set up so that we could solve for these 3 variables. Okay. Okay, so you see one of my variables is N3 over N2, so I just divide by N3 and N2, okay? Okay, so then I solve the system of equations. I get xb2, xbb. I'm sorry that this program keeps glitching. I'm not sure why. You get that the ratios are here, and then N3 over N2 is one of our things that we solved for up here, N3 over N2, right? And then we got N2, N1 over N2 by using, remember I said we were going to use that oxygen equation, right? This has N3 in terms of N1. Okay, so we just pulled this, I just pulled that, and I was able to solve for what N1 over N2 is using that equation, okay? All right, so then part B. It now turns out that the fuel mixture may contain not only propane and butane, but also other hydrocarbons. All that is certain is that there is no oxygen in the fuel. Use atomic balances to calculate the elemental molar composition of the fuel from the given combustion product analysis. What mole percent is C and what percent is H? Prove that your solution is consistent with the result in part A. Okay, so in order to do this, I'm making my own new variable here. It's called Q. So Q is the total number of moles of atoms in the stream. So normally if we're working in mass, I'll use an M. If I'm using the total number of moles of like molecules or components, I use N. And then I just decided to use Q. You could use any letter you want, or any variable or whatever symbol. I just use Q. Q is the total number of moles of atoms, okay? So it's very important not to confuse N with Q. Very different. N is the total number of moles of molecules. Q is the total number of moles of atoms. They are different, okay? Okay, so here's our balance with carbon. We say we have total number of atoms in stream 2 times the mole fraction of atoms, of carbon atoms. Okay, pretty simple. And then we do the same thing for stream 3. Oxygen, pretty easy, right? Once you know how to set that up, you just have Q times whatever component you're looking at. Q times whatever component you're looking at, right? Okay. In stream 1, we know that Y, the mole fraction of C, carbon, in stream 1, plus the mole fraction of hydrogen in stream 2 is equal to 1. Same thing with stream 3. We know that there's carbon, hydrogen, and oxygen in this stream. So if you add up all those atomic ratios, you get 1, okay? And now here comes the hard part. We need to convert stream 3 into atoms instead of moles of molecules like we have it before, okay? So if we say this is the total number of atoms in the stream, then we say, okay, this molecule, there are this many carbon dioxide molecules, and each carbon dioxide molecule has 3 atoms in it. There are this many moles of oxygen in stream 3, and each mole of oxygen has 2 atoms in it. There are this many moles of water in stream 3, and each mole of water has 3 atoms in it. Okay, so that's how you break that up. Then you do the same thing for the total amount of oxygen atoms in stream 3, and you do the exact same thing, you kind of break it down the exact same way. Same thing for hydrogen, and then you do the same thing for carbon, okay? Same concept used over and over. Then you can set these equations, substitute in these equations, like I did here for, as an example, for hydrogen. I did it for hydrogen there. Well, then you can see that hydrogen times Q, this is Q, just substitute that in, equals this, right? Equals this equation. Okay. The n's, the n3's cancel out, right? And then you can just solve for YH3. Okay, so now I have everything in terms of YH3, YC3, and oxygen. Okay. So that's how you solve for put it all in terms of atomic ratios instead of molecular ratios. Okay. Now that we have these solved, we have a system of 3 equations and 3 unknowns, right? And we just solve it the exact same way that we did before. Okay, 3 equations, 3 unknowns, solve for that. We have this solution, okay? And then you can use this, and same thing, oxygen. You can use the Q1, Q3 relationship in oxygen to solve for Q1 over Q2. Okay, so this one we solve with the system of equations. If we wanted Q1 over Q2, we could solve it using that oxygen relationship. That's where this comes from, okay? Now, second part of part B was, is the answer consistent with the answer in part 1? Okay, well, here's our answer from part 1, and here's our reaction equations from part 1. Well, let's convert stream 2. Let's go the other direction again. Same thing that we just did up above. We need to convert these and figure out what our atomic ratios are given these statements, okay? If those are our atomic ratios, then if these are our molecular ratios, then let's calculate the atomic ratios. There are this many moles of pentane in there. Each mole of pentane has 3 carbon atoms in it, right? Each mole of butane has 4 carbon atoms in it. Each mole of pentane has 8 hydrogens in it. Each mole of butane has 10 hydrogens in it. And if you put it all together, there are 11 atoms in pentane, and there are 14 atoms in butane. Okay? Then we do the same thing. You can just divide. The N2s cancel out. And then we can solve for the atomic ratio of carbon in stream 2. And it equals this. And the atomic ratio of hydrogen in stream 2 equals this. Now, do those match? You can see by my check marks. Indeed. Indeed, they do. They do match. Okay? So that is it for problem number 4.73. Thank you for watching. Hope you guys have a great day, and please like and subscribe. The more people that do that, the more I can keep making these videos. Thanks for asking questions. Hopefully I got this out to those who were wanting to see this to help it make it so that it was useful for them. All right, I hope to see you in the next video. Thanks.